Hello, I'm again Dr. James Wotton of IBM Quantum. This is again a lecture on quantum computing, but what is computing? Well, a very simple model for what a computer does is it takes an input, let's call it x, and then it computes a function, let's call it f of x, to give us an output, which we can call y. And in a digital computer, all inputs and outputs can be expressed as binary strings. So this is a function which takes in binary strings and outputs binary strings. In general, those binary strings can be different lengths. So we can have some input bit string with some ni bits. We can have an output bit string with some no bits. And in the middle, we can think of the computer as basically just being a black box which takes the input in and spits the input out. So there we go. There's our spitting out, and here's our taking in, and that is our computer. Okay, it's not a black box, but you get the idea. So if we can implement a general mapping from inputs to outputs for a general function in this way, then whatever it is that we are using to do that, we can call universal. So if we can use, for example, NAND gates to perform any general mapping of this way, then we can say that NAND gates are universal for computation because they can do any of these general computations. Any function you want, any number of bits for inputs and outputs, you can find some configuration of NAND gates which does that. Now it's easiest to prove this, I won't prove it explicitly, but it's easiest to prove this if we think of implementing the computation through a lookup table where we're basically writing down the program which says if the input is some particular input, then output the corresponding output. But this is kind of, well, a terrible way to write a program because A, you need to have as many lines in your code as there are possible outputs. You need to go through possible inputs. So you have to go through all of the 2 to the ni possible inputs, which obviously goes up exponentially with the number of possible inputs. And also, you need to know all of the answers already. But nevertheless, it's quite easy to show that if you have things like Boolean logic gates, you can do the process of checking all of the values to see if these conditions are met, and if they are, then writing down the correct output. So we can show that these Boolean logic gates are universal because they can reproduce any of these functions. Okay, actually, before we move on, let's look at a few possible functions it could be, just to be a bit more explicit and a bit less concrete. So we could have an input which is something like 3 times 5, so binary representations of the numbers that are going to be multiplied. If your function is just a function that does multiplication, then that's all you need. If you have a more general computation which could do any kind of maths, then you might also want a binary representation of the fact that you want to do multiplication, to tell your function that, to tell your computer that. And of course the output in this case would be 15, but you also might have something where your input is an image, for example, such as a picture of a cat, and then your output could be something like a very simple binary yes or no of whether this image contains a cat. So in this case, we would hope that it is kind and gives us a 1, but if we had an image that doesn't contain a cat, it would give us a 0. So these are just a few examples of the many possible ways that you could have a computation. And in this latter one, it's obvious that if you've got a computation like this, you do not want to do it by a lookup table. You do not want to go through every possible image there could ever be and decide whether there's a cat in it or not, and then write a lookup table which looks on that list to see if it's a cat there. You want to do a computation. You want to process that information in order to work out what input to give. And once you do that, you get into the weeds of what is actually computable, and we're not going to go into that sort of thing at the moment. We're just thinking more specifically of a notion of universality, which is computation as a function, and when do we have the ability to implement those functions. Right, now let's start talking more specifically for quantum computing. And in quantum computing, we do computations by unitary gates, and unitary gates are reversible. So we're going to have a bit of a different definition of what a computation is in order to suit this reversibility condition. Specifically, we're going to want to define computation as something which takes an n-bit input and gives an n-bit output, where the n is the same in both cases. So this would seem like a more restrictive version of the definition of a computation that we had before, but it isn't necessarily so. Also, we want it to be such that each unique input gives a unique output and vice versa, which again seems a bit more restricted. But again, it's not necessarily so. We can just choose our n to be large enough to forgive all of the sins. So specifically, we take our n to be what is our previous n input plus n outputs, and then we can have our computation as taking in not just x, but x with a bunch of zeros, which represents some blank variable where we're going to write our output, and then the output is a copy of x with the output written on the blank variables. So here we can see that every unique input does have a unique output, and that is enforced in a very simple way by just having a copy of the input in the output. So if we were to take reversible gates and implement a function like this, so for example, you could take a computation which just takes an x and turns it into an f of x. You could compile that into NAND gates. You could then implement that with TOEFLs, which are a reversible form of the AND NAND gate. And then you could implement that function in this way, where you keep a copy of the output, and you'll find that it is also reversible in that each unique output has a unique input. The fact that that is happening is because you're making it out of reversible gates, and that just enforces this condition naturally. Okay, so let's now write this in a more quantum form. What we want out of our computation is the ability to take an input that can be expressed as an input state x, which is a bit string, but we are writing this bit string in qubits. So if it's an n bit string, an ni bit string, then we use ni qubits to write this down. So this is a tensor product of ni bits actually hidden within this simple looking x. We tensor product that with a bunch of zeros, specifically no zeros, and so we use this power and a tensor product notation to show that we are taking a tensor product of no zeros, and we want our computation to be able to take such a state and rotate it into a state which again has our input expressed as a bit string, but also has the output expressed as a bit string. And since it's a reversible process, this can be implemented by a unitary. So we basically want to find unitaries that can provide this sort of rotation. So If universality for classical computers means the ability to implement any function y equals f of x, giving us an output y for a given input x for a given function, then universality for quantum computers could mean to implement any unitary UF, which is an n-qubit unitary acting to reproduce this function, to take a bit string expressed in terms of qubits and write down a corresponding output according to what this function is. So for any possible function, for any possible number of qubits, if we can create these corresponding unitaries, then we can say that we can reproduce computation in exactly the same way as a classical computer can do computation, and that we are universal. So the ability to implement any arbitrary unitary like that is what we need to do to say that we are in some sense universal. However, the restriction that we should create unitaries that can reproduce these sort of binary function things is an unnecessary complication. So to say that we want to create unitaries that can do this specific job is not a requirement that actually makes anything any simpler for us or makes anything make any more sense. Really, we can be much more general and much more simple in our definition of what unitarity means for quantum computers. So unitarity means that we can reproduce any arbitrary unitary acting on n qubits. For any number of qubits, if we can find some way to implement any arbitrary unitary, then we have what we would call a universal quantum computer. And it is just a consequence of that we could use these unitaries to implement these classical computations, and therefore we could, in theory, run everything from Excel to Mario Kart. But the fact that we're defining it in terms of unitaries means that also we can do more general things. But in this lecture, what we want to prove is that a gate set that we have already seen is sufficient for universality. It is sufficient for reproducing any unitary and therefore can reproduce any quantum computation. It can be used to implement any quantum algorithm or indeed any classical algorithm. So let's get on with doing that. So I'll just remind you of something we looked at last week, which is a certain gate set where we had rotations around the x-axis, and we could actually use rotations around any axis, but we were looking specifically at rotations around the x-axis by some angle theta, as well as the Clifford gates. So this could be the Hadamard, the S dagger, and even if you don't explicitly have the S dagger on its own, you can make that out of S's since it's S cubed, and the controlled knot. There are different ways to express generators for the set of Cliffords, but this is a good one. So yes, these are the Cliffords, and this is our non-Clifford, and together they give us everything. And the first step towards everything is to note that the Rx can be expressed as e to the I theta over 2x, and by using the single qubit Cliffords, we can transform this into e to the I theta over 2y, or e to the I theta over 2z, or e to the minus I theta over 2x, and so on and so forth. But by using the 2 qubit Clifford, the controlled knot, we can turn this into a 2 qubit gate, such as e to the I theta over 2 x tensor x. And therefore we can turn that into x tensor z, y tensor x, and so on and so forth. And we can get to the point of expressing this as e to the I theta over 2 p, where p is some general n-qubit Pauli. So it's the tensor product of some Pauli on qubit n-1 all the way down to qubit 0, the first qubit. And these Paulis are all either X, Y, Z, or identity. So we have the ability to create a wide set of multi-qubit Paulis in this way, but not every unitary can be expressed in this form. So we need to have the ability to represent unitaries expressed in other forms. And the simplest one is where we just take e to the I and then theta over 2 of some Pauli p plus some theta prime over 2 of some other Pauli p prime. That is not of the same form. So how can we use gates such as this to create gates such as this? Well, there's a naive approach. It doesn't work, but we can adapt it into something that does. So the naive approach is to remember from school that e to the x, e to the y is equal to e to the x plus y. And one way to prove this is to do the Taylor series of each of these things. So you can express e to the x as 1 plus x plus terms of order x squared. And you can express e to the y as 1 plus, sorry, this should be 1 plus x on its own. I don't know where that squared comes from. 1 plus y plus terms of order y squared. And you could actually go up to higher values if you want. And then multiply them together, and you find that this is 1 plus x plus y plus xy plus yx plus blah blah blah. And then you can compare that to what you would get for the Taylor series of e to the x plus y. And the important point is that you get these sorts of things here. So why have I written this as x times y plus x times x, when I could have more easily written this as 2 times xy? Well, it's because they commute is the reason why we can do this. And this is exactly the property that we need to be careful of when looking at relations such as this. So in our proof that e to the x times e to the y is equal to e to the x times y, if we continued on this, and I'm not really going to look into it in detail, I'm just highlighting the point where the issue would crop up. If we were to try and prove it in this way, we would explicitly be using the fact that these two things commute. So when we are given this relation in school, we're given it for numbers, and the fact that multiplication commutes for just normal numbers is so ingrained in us we hardly even think of it. But when we have matrices, then we have to be more careful. Matrices do not always commute, and so this relation only holds in those cases where A and B commute. And this is not true of Paulis in general. Sometimes Paulis commute and sometimes they anti-commute. So, for example, x and y anti-commute, and therefore, where did that A come from? And therefore, e to the x times e to the y is not equal to e to the x plus y. Okay, so that's why it doesn't work. Now let's see why it does work. So explicitly what we would want is that the unitary that we're trying to get, which is this e to the I, let's write it down here. So this e to the I, and then theta over 2p plus theta prime over 2p prime. What we would love is for this to be equal to e to the I theta over 2p times e to the I theta prime over 2p prime, since we have the ability to do this game and we have the ability to do this game, and so just by doing them both we would be able to create this unitary. However, it doesn't work because they don't commute in general. But what we could do is take the nth root of both sides for some sufficiently large n. So we take the nth root of that, we take the nth root of that, and you take the nth root of that. So this is equivalent to, instead of doing theta over 2, to having theta over 2n, and so on. So just making the angle much smaller. In that case, what we find is that these actually do become approximately equal. Although this isn't a very strong statement, because if you take some unitary to the power of 1 over n for a sufficiently large n, then as n goes to infinity, this basically becomes u to the power of 0. And u to the power of 0 is the identity. So what we are saying in that case is that for a sufficiently large n, something that is approximately equal to the identity is approximately equal to something that is approximately equal to the identity multiplied by something that is approximately equal to the identity. However, what is a stronger statement is that if we take the nth power of both sides, then the approximate relation still holds true. So this is the nth power here. If we take the nth power of u to the 1 over n, you just get back to u. So now we have an approximate form. And more explicitly, if we want to write this down as this being equal up to some error term, then for any arbitrarily small value of the error term, the value of n that you want to get such a small error, it increases polynomially with 1 over delta. So it's not just that it's approximate, but it's also you can get as close as you want by just choosing the right number of repetitions, and that number does not scale horribly. It's not going to ask you to do too many repetitions. So this is a way of taking gates of this form and combining them to make gates of this form. And this is known as the Trotter-Suzuki method. So we basically just take very tiny little slices of those gates and put them in order, and then repeat this many, many times. The more repetitions we take and the tinier the slices are, the better the approximation. Okay, so that is sufficient for explaining how to do it for this specific one where we have two Paulis, but more generally we will have more in here. So let's go now towards the final goal, which is to show how to reproduce any unitary. So any unitary can be expressed as e to the I h times any Hermitian matrix. And a Hermitian matrix, like any matrix, can be decomposed into a linear combination of Pauli's with some corresponding coefficients. And one thing to note is that if you take the Hermitian conjugate of a linear combination of matrices, you get the linear combination of their Hermitian conjugates. So we just take the Hermitian conjugates of these Pauli's, and if there were coefficients in there, we take the Hermitian conjugate of those coefficients, which for numbers just means the complex conjugate. Now, since H is Hermitian and therefore equal to its own Hermitian conjugate, and since the Pauli's are Hermitian and hence equal to their Hermitian conjugate, then these relations only hold if the couplings are also Hermitian, which for numbers just means they have to be real. So a general unitary can be written as e to the ih for some h, which can be expressed as a linear combination of n qubit Pauli's with some coefficients which are real. And this means that we can then decompose each of these terms as one of these e to the I theta over 2 pj's, where we are just using theta over 2 as the corresponding coupling jj. So if this is a theta j for a specific j. So by just setting these angles to be the right values, we can come up with a gate which corresponds to each of these terms. Using the Trotter-Suzuki method, which we just looked at for 2 terms, we can actually use this for any number of terms. And we can stitch together all of these terms and we can come up with any arbitrary unitary. And so there is basically our result. Using single qubit rotations, like the rotation around the x-axis by an arbitrary angle, as well as the Cliffords, we can make these big multi-qubit e to the I theta over 2 Pauli gates. And using the fact that a unitary can be written as an e to the I Hermitian, and the fact that a Hermitian can be written as a linear combination of Pauli's, then with the Trotter-Suzuki method and these gates that we've created, we can recreate any unitary. Now, this is not necessarily the best way to recreate any unitary, and you shouldn't have as your first tactic in writing any quantum algorithm that you first come up with the unitary that corresponds to the algorithm, and then you try and reproduce it using the Trotter-Suzuki method. This is not going to be the best way in general. It's kind of like the bad method of programming I gave earlier, which is to write down an exponential number of conditional clauses. So it's not necessarily the best way, but it does prove that the gate set is universal. And so we can proceed with gates like rotation around the x-axis and the Cliffords, knowing that anything that a quantum computer can do can be done using those gates. So if we make our algorithms out of those gates, we are not going to be missing anything. We are not going to be missing out on fancy quantum features that are otherwise possible, because any quantum computation is a unitary, and any unitary can be made out of those gates. They are a universal gate set. There are also other gate sets that are universal. For example, you could also have the Cliffords plus anything that is non-Clifford. So you just take the Cliffords and you take anything that is not a Clifford gate. So it's not necessarily like the rotation around the x-axis. That's something that's not a Clifford gate, but it's actually an infinite number of gates, because we could have any possible angle in there. But we could take any. For example, the T gate, which is the rotation around the z-axis by an angle of pi by 4. If we have the T gate, as well as all of the Cliffords, we can also prove that this is universal. And it's a bit of a horrible and awkward proof, so we're not going to do it here, but you can do it. And one that I think is even more surprising is that another universal gate set is the Toffoli, which you may remember. Since it can do the and the NAND, it's essentially universal also for classical computation, or you need to have bits initialized in ones to unlock the NAND power, but nevertheless, we can think of this as universal for classical computation. And the only thing you need to add to that to make a universal gate set is the Hadamard. So using these two things together, you can do any arbitrary single qubit rotation is what is implied by that, which is like kind of mind-blowing. How does that work? It's not necessarily how you want to build a quantum computer, but the very fact that it can be proven that this is universal is an interesting fact. And also the fact that Clifford plus anything non-Clifford is universal is actually used quite a lot in our plans for fault-tolerant quantum computation, because due to reasons that we will look at a little bit more later in the course, it is quite easy to build versions of Clifford gates that are hardly affected by noise, that we can very easily identify and remove any imperfections. For non-Clifford gates, it is much harder, especially if you're talking about a continuous rotation, such as rotations around the x-axis by some angle, because rotation around the x-axis by that angle is a valid gate. Rotation around the x-axis by that angle plus some infinitesimal amount is also a valid gate. So how do you distinguish between this valid gate and the valid gate which is a slight over rotation? It's a very difficult thing to be able to distinguish between two valid things that are continuously related to each other. But the fact that we can just use a single non-Clifford gate means that all we need to do is hone the ability to do that one thing perfectly. And if we are a very slight over rotation from that gate, then that is incorrect and needs to be corrected. And then we just use that one gate that we can hone perfectly in order to bring in all of the non-Cliffordness that we need in the computation. So that's enough about universality. We have now proven that our quantum computer can do everything. What remains is to prove that it can do specific things, and also that it can do things better than a classical computer. Now, one example that we can use as a motivating example of a quantum computer doing something better than a classical computer actually uses exactly the same example as we've used to prove universality. So in physics, there are various physical systems that we might be interested in. One is that of spin-half particles, like the electron. So these have a property called spin, and the spin is described by a two-dimensional quantum system, which has states of spin up and spin down in each of the normal real-world directions. We also have photons are another important particle. They are described in terms of their position by a continuous quantum variable, but they also have their polarization, which is described by a discrete quantum variable. So you can have polarization in the vertical or horizontal directions. Those are two orthogonal states. And then a valid basis is the polarizations at 45-degree angles from those. And then another valid basis are the circularly polarized states. So this is another two-dimensional quantum system. And of course, our favorite two-dimensional quantum system is one that is not a physical one, but is one that is abstract. And that is the qubit, defined by states 0 and 1. Or at least that is the Z basis. There's also the X basis, which are the plus and minus states, and the Y basis. And, well, what a coincidence. They're all written here. So this is just to impress upon you that the mathematics, the theory behind qubits is exactly the same as the theory behind spin half particles. And that's one reason why some approaches to building quantum computers seek to use spin half particles as qubits. And it's also the same as the theory behind photon polarization. And that's why some approaches to quantum computing seek to use photon polarization as a qubit. So if you want to do the physics of a bunch of spin half particles that are just sitting, say, on some sort of square lattice, interacting with each other according to what their spin values are, then that is something that we can seek to represent on, we can seek to represent it on a classical computer, or we can seek to represent it on a quantum computer. Now, which is going to be best? Well, the length of the ket, so the state vector for n spin half particles. I've used n for something else in these lectures, so I should actually use little n. So the number of numbers that we have to write down is 2 to the power of n. So this scales exponentially. And that's just writing down the state scales exponentially with the number of particles. But how many qubits do you need to write down the state of n spin half particles? Well, you need n. So that's an exponential advantage, just because you're encoding the information in a system that it is more naturally expressed in, instead of trying to write it down in terms of classical variables. And then if you want to simulate the time evolution, on a classical computer, that means some process which still has to keep track of all of this horrible number of numbers. But in terms of quantum computing, well, the time evolution corresponds to a unitary. That unitary can be expressed as e to the I h, where the h in this case is indeed Hermitian, but it also is called h because it is the Hamiltonian. That is an operator which describes the interactions between these spin half particles, and it is naturally written as a set of interaction terms which can be expressed in terms of Pauli's and corresponding couplings. So the description of our problem is exactly one of these Hamiltonians, and what we want is this time evolution, and we know that with a polynomial number of gates we can simulate this to arbitrary accuracy. So simulating the time evolution of a quantum system is a computational problem. It's one that would take exponential resources in general for a classical computer. That's assuming that there's no special symmetries to the problem which allows us to do everything in a more simplified way. But for a quantum computer, because it naturally speaks the language of spin half particles, then it is able to do it in a much more efficient way. So we've shown that quantum computing is universal and how to get universality, and we've also found a motivating example of a problem that a quantum computer could do better than a classical computer. So now we can study more generally what quantum computing is, how it approaches problems, and what advantages it can have over classical computing, and ones that are relevant for physics and chemistry relating to the actual physics of problems, where the quantum of the computer is doing the quantum in the problem, but also more broadly and more abstractly for problems that have nothing to do with physics. Now, as we go into some of these examples, and especially some of the early and simple examples of quantum computing having an advantage that we will go through, we will learn about the concept of an oracle. And the oracle is just a fancy way of saying times when we need a quantum computer to do classical computation within, so as a part of its quantum computation. And the classic forms of oracles are known as the phase oracles and the Boolean oracles. And the Boolean oracle is exactly what we saw earlier. So let's call that UFB. And it takes an input encoded in a bunch of qubits. It takes a bunch of blank qubits. So let's do that to the power of NO. And it turns this into the input, again unchanged, but a copy, also the output written on the other register. So we've got two quantum registers, one of Ni qubits, one of No qubits, and it effectively doesn't do anything to the register that encodes the input, but it does do something to the register that encodes the output. And the reason why we need to represent this quantumly is because there are times in computations when we will want to act not just on some single x, but on some superposition of x's in order to get interference effects. And so we will start off with this superposition state, and we will want to get out a superposition of different outputs. So now it's just, well, the same as up there, but in the sum. So that is a Boolean oracle. Now also the other kind is a phase oracle. And what a phase oracle does is it acts upon a register of qubits encoding the input, and it gives us back the same register of qubits in the same state, but with a phase. So when you just apply it to a single state like this, it's a global phase and so has no effects. But when you apply it in a superposition, so a case such as this one, it becomes a relative phase, so it does become relevant. And the phase is not -1 in all cases, but is actually -1 to the f of x. And in this case, we usually assume functions where we just get a binary result out. So like pictures of cats. So this is either a 0 or a 1. And if it's a 0, then this phase is -1 to the 0, which is +1. And if it's 1, then it's -1 to the 1, which is -1. And even though these two kinds of oracles do look quite different, they are actually quite similar, and we can use Boolean oracles to implement phase oracles. So the way we do that is to take a Boolean oracle for a given function and apply it to the state which has the input that we are interested in, tensor producted with the minus state. So why is this? Well, the action of the Boolean oracle is one which takes x tensor 0 and gives us x tensor 0 in the case that f of x is 0, and gives us x tensor 1 in the case that f of x is 1. So it's kind of like a generalized form of the controlled knot, but instead of it just looking at the control qubit and seeing if the control qubit is 0 or 1, it instead looks at the control qubit register and sees, is this an x that would give me f of x equals 0, or is it an x that would give me f of x equals 1? And in the case that it is an x that gives you f of x equals 1, then it applies an x to flip this from a 0 to a 1. So it's sort of like a general form of a controlled knot, because in this specific case it is applying an x to the 0. Now we know that if you apply an x to the minus state, what you get is the minus state with a phase of -1. So by doing a controlled knot here, then what the control is doing is either doing nothing to the to the minus state and therefore getting no phase, or doing an x to the minus state and getting a phase of -1. So what we find is that when we do this, then the result that we get out is in fact minus 1 to the power of f of x, because it depends on whether this phase has been induced or not, times x tensor producted with minus. And this minus remains unaffected, which means that if the x part was in superposition over here, it would also be in superposition over there and would be unentangled to the minus. So from this we can effectively just ignore this whole part, and we find that using this phase kickback method, we mean that the Boolean oracle is having the effect of a phase oracle. So in the cases where we need phase oracles, if we can implement a Boolean oracle, then we can get ourselves a phase oracle too. However, how do we implement a Boolean oracle? So I implied earlier that the ability to do a classical computation which takes a given x and gives you back the corresponding output f of x is sufficient to also do a quantum version, because you can just take the program that implements that, compile it down into NAND gates, replace those NANDs into Toffolies, and it would give you something which takes x and a bunch of zeros and gives you f of x, or x tensor producted with f of x, and no zeros, because the f of x is written over the zeros. However, this is not quite true, because one thing that we often forget is that in our classical computations we often use in the course of our program variables that get ignored over the course of the computation. And this, if we take it into account, will come as what we could call garbage. So these are the undeleted remnants of a computation. So in classical computation, it's perfectly fine to do a deleting operation, something that, if we expressed it in quantum terms, would keep a 0 as 0, but would turn a 1 into 0. And such an operation is not Hermitian. It can't be realized by, not unitary. It can't be realized by unitary gates. And if we wanted to do this in a computation, we would have to use something like measurement. You could measure a qubit, and if it's 0, do nothing. If it's 1, flip it down to 0. Or in a case where the 0 and 1 states are physically have different energies, you can let it interact with a thermal bath and let it cool down to the 0 state. But again, this is something that is similar physically to a measurement. It's almost as if the thermal bath is measuring and then deciding whether to take the energy out. So this will not sit very well with any interference effects you have. Lots of quantum algorithms use delicate interference effects, and by using non-unitary gates you will mess up interference effects. So we need some way to get rid of this garbage, because this garbage is also, as something that we don't want, it's also going to cause troublesome effects in the interference effects that we need for the algorithm. Okay, so let's assume that we have a unitary U which does this. Well, when we have a unitary, we typically also have the ability to do the Hermitian conjugate of the unitary, because whatever sequence of gates is in our unitary, so let's say our unitary is a sequence of 2 gates A and B, then as long as we have the ability to do the Hermitian conjugate of those gates, then we can just reverse the order of the gates and do the Hermitian conjugates instead, and we get the Hermitian conjugate. So usually when we have the ability to do a gate, we have the ability to do the Hermitian conjugates as well. And this means that we have the ability to take something that has some garbage and delete the garbage in a unitary way, because by taking this x, f of x, g of x, and applying the the Hermitian conjugate of the computation, we get x and then a bunch of zeros, both for the register that would contain the output and also the register that would contain the garbage. So we have got rid of our garbage, but at the cost of also getting rid of our output, which is a problem because we need the output. So for that, we can think, well, before we uncompute, as it's called, in order to get rid of the garbage, why don't we just copy paste our output? So for that, we need to be careful because there's this notion of the no cloning theorem. So does there exist a unitary which can be applied to a state, let's just say a single qubit state at the moment, as well as another qubit in a well-known state such as 0 that can create two copies of that state? And the answer as to whether this is possible depends on what this is. So if we very well, completely and utterly know what this state is, then this is fine. If we know what this state is, we know a unitary that can create that one specific state. And so all we have to do is apply it to this other qubit, and then we'll have two of them. However, if we have no idea what the state psi is, and we want to create one single unitary which can be given any arbitrary state psi and copy it, then that is not possible. There is no unitary that can do that. And this is known as the no cloning theorem. So there's two extremes. If we know exactly what the state is, if we're designing a unitary for one specific state psi, then it's possible. If we're designing a unitary that should act on any arbitrary state psi and copy it, that's not possible. Another case in between these two extremes is when we want to design a unitary which is going to take a partially unknown state. So we may know that it is, for example, either 0 or 1, and we want to create a single unitary that can copy a 0 or 1 without having to design a specific one that will copy specifically a 0 or a 1. Now in the case that we know that it's going to be one of a orthogonal set of states, then we can do this. There is a way of copying an unknown state from a set of orthonormal states. And in this case, the unitary we would need is one that is actually well known to us. It's the controlled knot. The controlled knot is a state which, when given 0, 0, gives us 0, 0. And when given 1, 0, gives us 1, 1. So whatever is on the control gets copied onto what is on the qubit of the target, assuming that the qubit of the target is initially in the state 0. So we can copy bits. That is something that's perfectly valid. So we can then do a process in which we initially have a register of qubits with our input x, and then a register of qubits with a bunch of zeros, and then another register of qubits with a bunch of zeros, and then another register of qubits with a bunch of zeros. And then we can apply our computation with our unitary u, which gives us our initial x again, but overwrites the second bunch of zeros with our output, overwrites our third bunch of zeros with the garbage, and overwrites the sixth bunch of zeros with nothing because it doesn't actually act upon those. Then we can apply a bunch of controlled knots to each of the qubits in this register and this register. So for the first qubit in this register, we apply a controlled knot controlled on that and targeted to the first qubit in this register. Then another controlled knot controlled on this and targeted on the next qubit of this register, and so on and so forth, copying our f of x bit by bit until what we have, so I should say to the power of the n out, this is now x, f of x, g of x, and another f of x. Then once we've got the copy of our output safely in the bag, we can apply uncomputation to undo the computation, going back to just having x and then a bunch of zeros and then a bunch of zeros, getting rid of the unwanted garbage, and then this leaves our copy of the output where it was. And then the entire effect of this is to do the Boolean oracle that we wanted to do if we just rejig the registers. So with any classical computation, with the ability to do any classical computation and compile that down, say, into NAND gates, we can then use this uncomputation trick to do the corresponding Boolean oracles and the corresponding phase oracles. So when we come across quantum algorithms that require oracles in the next few sessions, you will know exactly how to do those, if you wanted to get into the details of actually doing them. When we're designing algorithms, we often leave that as an exercise to the reader, or at least to the person who's actually going to implement it once we get fault-tolerant quantum computers. But also you've seen in this lecture that we can do universal gate sets using just a few simple gates like rotations around the x-axis for a single qubit, as well as the Clifford gates, and with those we can do any computation. So now it just remains for us to look at specific forms of computations, which is what we will be doing in the next few sessions. But that's all for this time. Thank you for listening.